Here we're going to derive the basic kinematics equations using calculus, but starting only from the basic definitions. So I'm going to write down our definitions. Acceleration is just the derivative or the rate of change of the velocity. I'm going to put 3 lines there because that is a definition of what it is we mean by acceleration. In addition, we have velocity is defined to be the rate at which position changes. And using that in calculus alone, we're going to derive the basic equations. However, we do need a little more information. Namely, we need to have our so-called initial conditions. Namely, we're going to have an object that at time t0, which we're going to define to be when we start our stopwatch at t equal to 0, we will have the initial velocity will be v0 and its initial position we'll call x0. And we will only consider the condition under which the acceleration is itself constant. From those, we're going to derive 3 of the 4 kinematics equations. The 4th one is just a little bit of algebra. So first we're going to derive one of them using the acceleration. Once we know the acceleration is constant, we can rearrange this term right here to simply say that dv, the change in velocity over an infinitesimal small period of time, is just the acceleration times that infinitesimal period of time. Then what we want to do is basically add up all of these small infinitesimals. So we're going to integrate this by adding up all the small pieces, and we're going to make this a definite integral. We're going to start at time t equal to 0 and end at some time t. And then what we want is to find out what was the velocity at this time, and that was v0. So these 2 limits match. These 2 limits have to match too, so this will be our final velocity. Now we have 2 definite integrals to evaluate. The first one over here on the left-hand side is just integrating a differential. So this right here is just v evaluated at the 2 limits of v0 and v final. Over here we can say this right here is a constant, and constants we can take outside of the integral. So that's just the integral of a times the integral of 0 to t of just dt. And again, that is just integrating a differential. So this is just equal to a times t evaluated at the 2 limits. Now what we can do is just write these out. And this first side here on the left-hand side is just v final minus v initial, because you evaluate the integrand at the final minus the initial. And that then equals the same thing over here, which is just a times t minus 0. So that's just a times t. Now we can just solve for the final velocity, and that's just equal to the initial velocity, bring it to the other side, plus acceleration times time. And this right here is one of our basic kinematic equations. So we have derived that one. The only difference is we often call the final velocity just v rather than v final. Now what we're going to do is derive the next kinematics equation using our definition for velocity. Where velocity is just defined to be the rate of change of position. And again, we can rearrange this to say that a small change in position is just the velocity times a small infinitesimal period of time. Now we already found what the velocity is a function of time, so we can just say this right here is just the same as dx equals, and here I'm just going to write in the expression we had for the velocity, v0 plus at times dt, and this right here is just the velocity as a function of time. Now again, we're going to integrate this, and we're going to integrate this from time t equal to 0 to some later time t of v0 plus at times dt, and that equals the same integral over here for dx, and this will be x0, so these 2 limits match, and this will be the final position, so these 2 limits match. This is where it was at time t, and then the bottom is where it was at time t equal to 0. Now again, we have two definite integrals to evaluate. And we're just going to note the first side, the left-hand side, is just an integration of a differential. So this is just x final minus x initial. And that equals this integral. Now here we need to separate this out. So we actually have two integrals here. This is the integral from 0 to t of v0 dt plus the integral from 0 to t of at dt. So we have two integrals to evaluate. The first one is a simple one because v0 is a constant. We can take v0 outside of the integration. Then we just have an integral of dt. So the first term is just v0 times t minus 0, so that's just t. The second one, we have a as a constant. We can take that out. T is not. So we have the a times the integral from 0 to t of t dt. That is just finding the antiderivative of the function t, which is just t squared over 2. So this right here is just equal to v0 t plus a times t squared over 2 evaluated at the limits. So that's going to be a times t squared over 2 minus 0. So now we end up with our final equation. And we'll go to a new slide for that. And that is x final minus x initial is equal to v0t plus 1/2 at squared, just rearranging terms. So now we have our second equation. So what we have now derived is basically what I have labeled as the first and the second equations for kinematics. The third one is just the v final squared equals v initial squared plus 2a times delta x. This one right here just comes from algebra. And that one I've derived in another video, so I'm not going to rederive it here. The last equation says that the average velocity is the initial velocity plus the final velocity divided by 2, which is equal to the total displacement divided by the total time. Now, the last term in this, namely this right here, this is just a definition. That's what we mean by the average velocity. It is always the total displacement divided by the total time. This right here, we need to derive. That is not true in general. It is only true for constant acceleration. So the first part of this expression, we do need to derive. Now, that is something we argued in class makes sense, but now we need to actually show that it's true. And here we need to use a little bit of basic calculus. And what we're going to use is the function, the equation to find the average value of a function. So average value of a function is equal to average value on the interval AB is equal to the integral from a to b of f of x dx divided by b minus a. That's just a definition from calculus, and we're going to use our function right here. F of x is going to be basically the velocity as a function of time, which is v0 plus at, and x is actually going to be t, where a is going to be t0, which was 0, and b is going to be our final time, t. So with these interpretations, we're going to calculate the average value of the velocity. That will equal the integral from a to b, which is from 0 to t, of our function, which is v0 plus at, times dx, which is now dt, divided by b minus a, which is just t. Now, if we notice what we have on the top right here, that is in fact just what we evaluated right back here. It is this integral right here, which we've already done. And what we got was this expression right here. So we don't need to rederive that. So we can now just state that this right here is just equal to what we already derived, v0t plus 1/2 at squared, and that is all divided by t. Now that doesn't look like what we want, but it is. All we need to do now is show the little bit of algebra that this is the expression we want. First, we can cancel out some t's. So what we really have is v0 plus 1/2 at. And I'm just going to rewrite that and put them both under 2. So that's the same as 2v0 plus at all divided by 2. Now we've got the 2 where we want it. However, I've got 2v0 where I only want one v0, and I got an at and I don't want an at. But we can simply write this very straightforwardly as v0 plus at, that's just separating that out, divided by 2. However, this right here, we already showed that is the final velocity. So now all we need to do is substitute that in, and we have v0 plus v final all divided by 2, and that's what we wanted to derive. The average velocity over here is just equal to the arithmetic average of the initial and the final velocities. So long as this right here is the function that describes how velocity changes with time, and remember that right here was a consequence of constant acceleration. So this is true only for constant acceleration. So now we have derived all the formulas, and we'll just write them all down again. The first equation was just x equals x0 plus v0t plus 1/2 at squared. The second equation is just v equals v0 plus at. The third equation, which actually comes from algebra that we didn't do, is the final velocity squared is the initial velocity squared plus 2a times the displacement. And the final one, which we just did, is the average velocity is the initial plus the final divided by 2, which is just the displacement divided by the time.